So today I'm going to talk about a high level. Okay, thanks guys. So today I will talk about high level overview of Hypernova and possibly trying to skip all the math. Not because I try to dumb it down, because I do not get the math. That's why I skip all the math if possible. A quick brief intro as to what happened last week and as to why I chose Hypernova. Because last week we have gone through Nova, and a recap of what Nova does: introduction of IVC, and basically the introduction of folding schemes. And we have the concept of supernova, which kind of builds on Nova to be able for you to able to fold multiple instances, so that you can then have a smaller circuit that represents only a part of computation. That is Nova. It's very math friendly. It doesn't have a lot of math. Supernova is pretty math friendly. It builds a lot of concepts on Nova. And then we have Hypernova, which takes a bit of idea from Nova, but it changes the restrictions, because in Nova you are only restricted to RNCS, but in Hypernova, and Arun did a fantastic talk to do a prelim of CCS and how do you convert RNCS to CCS. You take in a CCS, a fold CCS, and to quick recap to what CCS is, in case you kind of miss a point among all the math. CCS allows you to represent RNCS, Planckish, and air. So ideally, should we able to write, for example, an air script or a Planckish representation, we are able to then use Hypernova to also fold. So now we can see that we are removing ourselves from the constraint of having to only use RNCS. We are then able to also fold Planckish and air. So this is why Hypernova is created. I'll keep this here because I like this. So the paper introduced this thing called the committed CCS, CCCS. This stands for committed. Similar to how Nova, they commit the witness and and also the M's in the CCS. Basically, you commit the M's. No, wait, M's not committed. Similar to how in Nova, you commit the witness, commit witness. Over here, they also uses the concept of committed witness to then move along in the paper. And there is another concept called the LCCS. L stands for yeah. I'm not joking. I'm not making this up. It's linearized. Okay, that's the end of everything. And what LCCS is? It's an equivalent of big U in Nova. And for those who recall what big U is the running instance. So we can sort of imagine that when we are folding CCCS together, and it will then be grouped together to this running instance, LCCS, just like how we are doing it in Nova. And this LCCS at the end of the day will then be the one that you will send to the stack, and then you prove the validity of LCCS, because this thing basically able to allow you to verify the computation of the IVC. So let's see how we do that. So I had a bit of help. I not only read the paper, I also watched a YouTube video by the great Sinash Sethi himself, and on the PSC channel. It was 1 hour 47 minutes. I know exactly how long it was because I already watched it. And a lot of the explainers of the math come from that video. So do not think that I understand all the math. I do not. So the video basically breaks down. Basically, we can imagine that given an CCCS, and this is a running LCCS, you are able to then fold this thing together to have a resultant. My handwriting is horrible. LCCS, right? So this is the general concept that we want to achieve. So the problem is this thing has to be separate into two parts. So you cannot just fold this I mean, obviously you cannot, but the way to do it is not like this. It's basically broken down into something like this, whereby you have two LCCS. I'll get to what LCCS really stands for later and why is it linearized in a bit. And this is our running LCCS, and then will be our resultant res LCCS. Okay, so and these two you can fold together easily using the normal linear combination. And however, the steps here, you then need to convert CCCS into LCCS. What is this? I can't remember. Oh no, this is not a diagram. The diagram is in the video. Now my laptop is over there. Oh no, what else going on? I'll make things up. So if it's not correct, my apologies. It's correct. No, something here is missing. I forgot what is it. Oh, wait, hang on. Okay, we'll find out. LCCS again, right? And then you combine this to form this, and then this one will fold.
Have multiple CCCS.
Oh, yeah.
And multiple LCCS, and then combine them together into
one LCCS, and then you fold it with the running LCCS instance. I pretend I understand that, but so the step here is not easy, not trivial, and I'll try my best to go through whatever I understand from the paper to sort of try to form this resultant LCCS, and then we'll see how we then fold the two the LCCS instances for resultant LCCS. So it's not trivial. So as we have seen in Arun's wonderful explainer of what CCS really means, and CCCS is just a complement over CCS. And LCCS is basically a dumbed down version of CCS. So CCS is NP complete. That means you can basically describe all computations in the NP problem to CCS, just like our RNCS and our AIR and our Plonkish. But LCCS is not. So it is, from what I understand, and from one of the questions that was asked in the video, the reason why it's not NP complete is because it basically only deals with additions. So basically, this is like my mental model of what LCCS really means is that it's like a simplified version of CCCS. It doesn't really allows you to perform all sorts of computation, but it's good enough for our running instance. That's how I would think of what LCCS really means. And how do you do this step? This is thing called re-random. If I recall correctly, that's a re-randomization step. And you have your partial sum check, which Kai has talked about. So I'll not go to partial sum check. No, I will not talk about this then. Actually, I will. Let's see. Sorry, I'm trying to find which page this is. Oh, one thing I will. This paper is like 40 pages long. I've removed all the knowledge soundness, completeness proofs, and also removed the n lookup at the end because I don't have time to go through n lookup and it's hard. And also this paper introduced the concept of n lookups, so you're able to perform lookups in Hypernova, something that you can't in Nova. So it's also an upgrade. But I'm not going through n lookups today. Perhaps one of you can. So, how do we do this step? So there is going to be like a prover and verifier in this conversion of CCCS to LCCS.
It's kind of multiple folding scheme here. It's a
Multiple folding schemes? Yeah, it's spot on. I don't get it. So I don't know. Is this folding? Is this folding? Or is just conversion? But this is a folding, yeah?
I think.
I assume this is step 3 of the paper. That's step 3 of section 5, step 3, I think. We can go through this after this. I do not know enough. So what is happening here is that it will run a sum check protocol, and then the bunch of equations that you want at the end. It's a what? Okay, this is where I have not prepared well. A C instance. Okay, this out. Should I copy? So, okay. So, the verifier will send prover two randomness from my understanding of this paper. One it's gamma and beta. So, basically it means two randomness. Beta it's in a few F and a S length. So first, what happens is that there's this QZ, the introduction of this QZ function, and this is where beta is going to be used. This is a multilinear extension of the equal operation. They just make it into an equation. So you can assume that this will be 1 only if these two are the same. So if the randomness, if this beta and x is the same, it will be 1. And then you'll take in a bunch of math here. And this is awfully familiar to the definition of CCS. So again, this is the constant of CCS, right? And there's a product. This are just small things that I just write for completion, but I don't M this x, y. It's too, oh fuck. Z to y. Let me try. So basically what is going on is that M is also being multilinear extended. So imagine these are equations have two variables, x and y. And then Z2 is the witness of our CCCS, right? And then the M's and the Z2 will go through a matrix vector multiplication to form one vector, and then it will then have a product over all the vectors.
So
huh?
maybe Z1?
No, it's Z2.
Z2?
Yeah.
Okay.
Yeah, it's Z2. Yeah, Z2. It's at page 18.
So Z2 is for okay.
Z2 it's the
is for this part linearized linear.
no, Z2 is CCCS.
CCCS?
Yes.
Oh yeah, sure. Yeah,
Yes. Z2 is CCCS. So this is a CCCS trying to get, and then so basically what you can see is that it's taking one randomness to sort of like in a partial sum check to sort of like convert this equation to a simpler form, Q's x. You can see. So at first it was xy, and thanks to our randomness, it becomes only x. That's why I understand from whatever. Okay, I don't really understand it, but Dr. Goh, feel free to say you're wrong. I'm more than happy to admit. And this is our LCCS part. Because LCCS has to take a randomness as well. Wait, hang on. I think Rx means the randomness of the previous round. I don't really understand that part. And so this step basically means that you are then using as well a randomness to form this LJ, and this is the LCCS part. So this is CCCS, LCCS, and the next part will be what we call the re-randomizing. So one thing that these two will need is that they need to have the same randomness. And this step that I'm talking about next will then make sure that this randomness and this randomness will be the same. It will be just g of x sum of j in t. Don't ask me what t is. Gamma j l j x plus gamma t plus 1 q of z. So you can see that q of z, CCCS, L of j, it's LCCCS, and using some randomness, gamma, you then combine it to our LCCCS. So this is, and then this will ensure that these two will have sort of like the same randomness because you use the previous randomness here and then use a new randomness here to ensure that this thing is going to have the same randomness. One thing that was asked in the video, which I think is worthy to highlight, in this case we are only folding one CCCS to one LCCS. You can also fold multiple CCCS as well, multiple. How this will change is that the Q will then have like I's indexes, and these are basically the same, right? And over here, you then fold it, it will then be combined to one LCCS. So this one you just have to do something like this: T plus 2, Q 2, X, and so on and so forth. So basically, this is just another trick of a linear combination of our QX, just like how we've seen in a lot of protocols, to form our LCCS. Yeah, so this step is this step, which is very important to get this, so that then you can fold these two together to form our resultant LCCS. Okay. Actually, I'm learning while doing this. Now it's clear enough to me. I don't know about you. I was like, oh, I get it. Yeah. Thank you, Dr. Go, and everyone for your patience. So, any questions? Good. Okay, cool.
Here the part just this part, right? It is a folding scheme.
Oh, okay.
It's a sum check based folding scheme.
Sum check based folding scheme.
Yeah, we have to build all of this into a circuit.
Okay.
Yeah, so it's within folding scheme. And for this part, it's also just
coming soon. Coming soon. Don't spoil. Don't spoil. Don't spoil. This one?
So we'll have to build that in a circuit. So we have it. So it's I think this part is bigger, much bigger than Nova.
So you need, okay, so this has to be in circuit, the sum shape.